So today we're going to talk about a mishmash of things. I got a whole bunch of different slides open, and kind of this latter parts of more different types of deep learning methods. And if you look at the deep learning book online, which I've kind of been switching to using more now the last couple of weeks, we went through kind of the topics in the deep for neural networks and some of the regularization methods. Last class we talked about convolutional neural networks, so we're going to kind of finish that up, and now we talk about more like if you do longer or larger CNNs, how do you make them work? And that'll go back to something we mentioned briefly before about regularization of models when you make them very deep. And then this kind of flows into, well, what if you didn't just have deeper networks, but networks span across time? So we'll mention that kind of briefly about how that works with time. And then if I have time, I'm going to start talking about this methodology chapter, because some people were asking yesterday about other ways to tune the hyperparameters of neural networks, which is a very important problem. And we have questions here even about how Alex is asking about how to divide up your validation and test sets. Old lecture links. Maybe that's why there's less people. Ah, no, it's pumped up. Right. Yeah, I think at some point the numbering might have gotten messed up. Oh, wow. Okay. Transfer learning attention. Yeah, so I'm going to delete the incorrect one. We're in the 12A one, right? Thanks for pointing that out. Error during edit of meeting. Yes. Sorry, I'm just going to update that so people see it. I can't delete it, apparently, but I can change the title. Oh, I can't change the title. Okay, so that one is incorrect. The one that we're in is the correct one. It'll be 13, it'll be next week, yeah. Some of the topics have been sliding a bit, and we had buffers, so that's exactly expected. But I guess I didn't move the date of it. I changed the name, but I didn't move the date. So hopefully if there's anybody over there, you can tell them to come over here, or they will figure it out soon. I can't tell if there's anyone in that meeting. So where was I? Yeah, so this practical methodology chapter, this is chapter 11 in that textbook, has a bunch of these topics covered in a fair bit of detail, and so we'll kind of flip through a few of those. But there's no super perfect answer. So yesterday we were asking about how to tune your hyperparameters, and there's really an entire set of methods, and it relates to some of this optimization as well. So we're using gradient descent to train neural networks right now with backpropagation. But the way you do gradient descent, obviously, that's an optimization method. So you can use any optimization method to train neural networks. You just have to kind of update them in a way that's kind of efficient. Gradient descent makes sense because of the way neural networks are set up. We don't know the structure. It's not a convex thing. But there's lots of tricks to improve it. And this methodology one also has other tricks about that. But there's no perfect answer. It's really trial and error and search for kind of the better settings. But there are some protocols. And then that relates to the validation test training set split as well. It used to be, you'd say, training data kind of like 80% validation, 5 or 10%, and test the rest. But some people, like Andrew Ng, and he's got a textbook that's very kind of practical top line topics for how to make your deep learning more effective. And that's a free online textbook he has as well, Andrew Ng. And I remember in that book he's talking about like how your test set should be like tiny, like 1% of your data, because if you have a large data set, just you improve more by training on more data, and then you test on something small. But that's very large data sets. So some of the rules about what these splits should be aren't even written in stone. Yeah, so this book has a lot of these other topics and answers, and then next week for the last couple of lectures, like I said, I'm going to try and record them this week, so you'll have them all online. We're going to talk a bit about autoencoders and about some of these other, I want to talk about attention and modeling, and there's a couple other low-hanging fruit from previous topics I wanted to add in related to that. Something I just found today with this textbook, because an annoying part about it is the textbook's free, but if you click on the chapter, say for convolutional neural networks, it loads as this fancy HTML page, which looks very nice. And if you print it, it doesn't necessarily come out as a very compact or good PDF. You have to figure out how to print it in your browser and play with the settings. But some person at this link has created a handy, perfect extraction of all the PDF chapters of it. And again, this book's free, so that's okay as far as I know. He just made it by printing them out individually, so you can look up that one. Yeah, I was surprised too when I saw, so people are responding on the chat about my thing about Andrew Ng's advice on test set training. You look up his book, I don't remember the exact number, but I remember watching the first couple chapters of it when it was coming out, and he was saying, oh, yeah, I shouldn't. Because if you have vast data sets, if you have millions of data points or billions of data points, that test set is still testing a very large number of examples, even if it's only 1% of your data. And the improvement you get on very deep neural networks, he argues, is preferable to spending a lot of your data and wasting it on dividing it up for validation. But I wouldn't necessarily advise that unless you know what you're doing and you have a lot of data. It's just to say that there's debate about that. Yeah, so it's not necessarily about the percentage, it's about how much data you have, right? Is your test set large enough to give you a sense that you've covered a reasonable number of examples, so you can be confident about it? But there is a trade-off of how much better will it get with another million data points versus how much you'll get for testing it with those data points. Pre-process. So another question about, do neural networks need pre-processing? What do you mean? You mean pre-processing the data like we talked about at the beginning of the course? Oh. I mean, it helps, so it's not 100% answer. I think technically they don't need it. If you have the right network, you could learn it straight from raw data that hasn't been altered. So a lot of, you do, in some ways, some less pre-processing than you do in maybe other methods, because it could just learn that this data is an outlier or not meaningful, but it could take a very long time for it to learn that, right? So pre-processing is still useful if you know the pre-processing you're doing is really going to shrink the problem, right? So for the text processing data sets, right, you remove stop words and kind of alter words to be kind of shorter forms of each other. In some data sets, you remove outlier noise if you know there's like actual noise in your sensor system and that some of them are just like errors. Removing them is going to help, because why would you force your model to learn them from scratch, right? But it has the flexibility to learn it, so that technically it doesn't need it. It's just, it might take you 10 times as long to learn it. But it's dangerous, right? If you do pre-processing that biases the data and creates new patterns that weren't there, it might learn something that isn't there, right? What they find, and we saw this with the data augmentation stuff, right? I guess, from the previous lectures. I think I'm going to have that one again. They're fairly robust, right? So if you throw some more stuff at them, they can usually adapt to it, at least when they're being trained at the scale that Google and them train them at. So if you change something or flip things, it can actually improve it, right? If you remember, one of the things we talked about in the effective deep learning part was data augmentation, right? So you take the input images and then you flip them and you rotate them and you add a bit of noise, right? So in that sense, it's like the opposite of preprocessing, right? You're creating new data that has noise in it, but you're doing this in order to create more variety. And it also increases the amount of data you have, which goes back to the thing Andrew Ng talks about. It's like, it's not the only thing that matters, but more data matters a lot, right? So even more data that is basically very similar to the other data, but slightly different in a meaningful way, can help your model get better because it's seeing more variety that helps it generalize, right? So if you're training it on images, and these are natural images of like the world, like we said, you can talk about, flipping them left to right, top to bottom, rotating them. Those are all things that you could see, and they're just as valid. And it forces the network to learn different filters, right? If you think about, this is a good one to think about, because it's almost, if you think of data augmentation is almost like the opposite of preprocessing and noise reduction, but it's being done in a particular way. Where was my slide on that? Oh, it's not there at all. Okay, I don't remember where it was then. Maybe it was in this data set. Yeah, I don't remember where my picture was. But that data augmentation idea was basically adding more data that has noise or rotations on it. But you can imagine then that the filters here, they're learning straight filters, right? Like a 5x5 filter that learns the response of, of a particular neighborhood of pixels around every pixel. You look at a neighborhood of 5x5, and this neuron here is learning some pattern amongst that, right? And if it's looking at cat images that are straight up, it'll learn a whole bunch of patterns, right? But now if you rotate all the images 45 degrees, you'd still would expect your model to detect cats that have their face sideways, right? Or at an angle. But none of the filters from the first training set might have learned that, right? And so now we'll be forced to learn something that generalizes to this perfectly reasonable situation, which is the cat's face is sideways. So that's kind of data augmentation is for that. No, yeah, and so I asked about data augmentation. You could do data augmentation on anything, right? So that's a general rule about neural networks, is that more data helps, and more variety of data that's reasonable transformations helps, right? So if you're doing sound data, like someone's asking, sound or voice clips, and trying to do, I was just judging a fourth year project course yesterday. Some of the undergrads here in UCE, right, they have their fourth year design projects. One of them did using an RNN type network, which I'll show you later actually, because it made me look it up, to do voice extraction from multiple, like in a noisy room. So if you have multiple voices at the same time, how can you kind of extrapolate, like focus out each of the voices separately and create their own wave files, their own sound files, where you can only hear one of the voices, even though multiple people were talking at the same time. This is what they were doing. And one of the things you could do with that is to do data augmentation, as long as there are reasonable transformations in that space, right? So if you have a sound file, you could move the waveform forward and backward, right? You could stretch it wider and narrower, right? Just means that the person's speaking a bit more slowly or a bit more quickly, or they said something a little bit out of order, right? All those things would be reasonable transformations that might happen in real data, and so you could just double and triple and quadruple your data set size by doing that. Because you don't want it to get hung up on that. What you really want, the data augmentation is trying to make it make your model learn something that's invariant to the important categories you're looking for in the data or the pattern. So you want to do transformations that make sense in that space. So we have a project where we work on medical imaging, so brain scans from MRI data, and we want to do data augmentation in that space, but we have to be careful we don't just use all the data augmentation things that make sense in visual images, because if you flip the brain left to right, it's completely different, right? Because the two sides of the brain are actually different, and you want to know which side's which. And so we want our network to actually learn that the left side of the brain has this pattern and the right side has this pattern. Not all pixels are the same, right? Every region of the brain has its own thing. So standard flipping and rotating maybe doesn't make sense, because really, once you normalize the location of the brain image, you want it to be the same. But adding noise and changing other structure would be valid, because those could be just variation in human brains, right? Cool. So are there other, I was going to ask if people have questions. So people had several questions, so that's good. We had our CNNs, and we talked a little bit about AlexNet, which is one of these first ones that kind of made it deeper and added more stuff. In those slides, we had additional other networks that kind of made waves for people. And they were all kind of trying to find ways to add more layers and improve performance. So this VGGNet is another standard one you'll see a lot as a popular method, because it's very effective. They had smaller convolutional filters, so they're using 3x3s, but lots of them. So whereas AlexNet had like 11 by 11 filters, so 11 pixel neighborhood, and then a whole bunch, like several 3x3 layers, but like 5 or 6. It worked well. VGG says, you know, we're going to have 3x3 layers, and how many filters did they have, right? So 96 filters, 256 filters, 300s, right? So remember, each of these 384 filters here means that there's 384 3x3 matrices of parameters. Each of these 3x3 matrices is convolved across the entire image, and it's a pattern that it's going to learn, like one of those edge detectors or an eye detector or whatever it's going to end up being. We don't actually tell it what it is. And there's 384 of those kept in parallel, and then those all get used to produce outputs, right? In VGG, they just had more, right? So 512 of these filters and build them up in a different structure. So this did even better on one of those competitions. And then there was this kind of war between Google and Facebook, I think, or Microsoft, on, well, let's see how deep we can make them, right? Very deep, hundreds of layers deep. And this is something that you can't do without very large computing power, but also you need to do some tricks to remove some of the problems that we talked about previously. And I'm going to go back to that slide deck, actually, to show it. Good question. So Jason's got a question about how you could take multiple types of input. For sure you could, and it's been done a fair bit. It's a good thing to talk about, actually. It's a thing that I don't have existing talks on. We actually have a project where we're doing that that we could talk about. Yeah, so I'll add that in as something to talk about. But basically, you have to basically build some middle layer that can interpret the two different things coming in and figure out how to merge them. But these three types that we're talking about kind of today of fully connected, we've talked about before, CNNs and RNNs are kind of your core patterns, and there's many versions within those. But once you have those, then you could say, okay, I'm taking a bunch of data that's coming from the census or from our COVID data like we have here for our project, and then you have a CNN that processes other images coming in, other data like maybe satellite images or face images. In the end, once you get to the point where this is a good way to think about it. A CNN is a type of neural network that turns image input using these convolution layers and pooling and other things into straight numerical output, right? So you go through some number of these layers for convolution and pooling, and then at some point you stop doing that and you're building this hierarchy, and you have this layer where you've got just numerical outputs, right? So from this point on, you've just got numbers. There are no spatial relationship anymore. They are some number of features that you decided. I'm going to have 500 features left at the end, and there are a bunch of numbers that describe this image, right? These types of images, right? And so we'll often then just refer to this thing now as the embedding, because it's kind of like, if you think of PCA and LDA, we talked about finding an embedding of an existing set into a lower dimensional subspace, but that is more meaningful. Or if you think of Word2Vec, we created a vector that we optimized all these weights to represent these types of documents. We called that an embedding. Now we've basically learned on a whole bunch of images doing classification, maybe, and embedding, right? But this part here, which is just a fully connected network that maybe does classification or whatever, it could be anything, right? So we could swap this out and put something else here. Once you've got numerical outputs, you can combine that with other data and have a fully connected network and do it. So we have a project that we're doing essentially where we have medical images coming in as input, and we have documents that are text, right? That are associated with those medical images. They're basically the reports that the doctors wrote, right? And we have some kind of CNN thing here, and we train it on, and then it's fully connected actually, and we train it on classifying on, can you detect which, human organ this came from, that this is kidney versus liver or something, right? And we train it, right? But then we take the embedding that we've got there and do that. And then so for this one we're doing, we're not doing Word2Vec, we're doing BERT and various other things. And we're trying to do some classification on diagnosis, I think. And then, but we can take that embedding out and train it. And so then what you can do here then is have another new fully connected network of however many layers you want, and then train it on your other problem, right? And so you basically freeze these ones and stop training them, and then train only this one. But then you can use the same two inputs and train it. But you basically build them up piece by piece and compose them together. As someone was mentioning, an autoencoder kind of does a similar thing, because you take some input data and learn output data, but it takes the same input all the time. So they can be used for this part after the fact. But yeah, so basically once you've got these components, you can kind of mix and match them. Okay, Jewel has another question. I'm gonna let that percolate in my head for a little bit, because it's a more complicated one, but it's about the softmax output. But let me move on a bit on our models for now. what did we have? Right, so this inception one I'm going to explain, because there's another one of these tricks, and it relates to our convolution thing. If you remember, so this is great. You want to have many layers, hundreds of layers. This one, I guess, had dozens, but each one of these boxes, so to understand this figure, Inception module. So they had max pool, so if you can't read it, I'm sure you can't read it. I can barely read it online. These red ones are max pooling. Oh, okay, that's what that is. Blah, blah, blah. Yes, okay. So each of these things is this this structure here, right? So it came up with this idea of having a multi-part structure to go from the previous layer and basically do convolutions of different sizes and pooling and then combine them together into one place. So why do they do this?